This is the introduction or first lesson on related rates. So we're going to talk about a couple of little details, do some warm-up examples, talk about some tips, and then do a few example problems. All of these are problems, like problem-solving problems, word problems. And so really it's about thinking, and it's about doing it yourself, not just an algorithm that you can follow. Every question is going to be a little bit different, but if you need some examples to follow, or the way we might present things, or some modeling of how we would solve these problems, that's what we're going to do here. So first of all, we got to remember what a rate is, and we talked about this in MHF. It's interesting to think about. Well, let's give an example of a rate first. So how about people like to use speed? We talk a lot about speed. So what's different ones for speed? Meters per second. And what about kilometers per hour? And so if I pick kilometers per hour, what is the rate happening here? Well, the kilometers is how much distance you traveled, and the hours is how much time passed. And together they form a rate, right? We consider the amount of distance in the amount of time, and the amount of distance can change and the amount of time can change, but it's the ratio of the two changes that makes the rate. So both of these are changing. And in MHF, we talked about the difference between an average rate of change and an instantaneous rate of change. So again, I think sometimes we take these ideas for granted because they're simple ideas, and we use them intuitively every day, but there is a bit more depth to them sometimes if we push ourselves to explicitly think about what's really happening. You can do this by visualizing the graph, by just, again, thinking about, well, what really is a rate? And thinking about it carefully. And sometimes that can help us connect with the problem that we're solving a little bit better. Okay, so, and there's lots of different kinds of rates. You can have rates that aren't involving time. A lot of them have time, but you can have rates. Another rate might be dollars per hour. So, how much it costs or how much you're earning. But here's one that doesn't have time. Dollars per kilogram is a rate. So if you're buying gravel or jelly beans or something like that, you might pay in dollars per kilogram. And sometimes usually it's with different units, but not always. It might be centimeters cubed per meter, or centimeters cubed per centimeter. Or it could even be, it seems a little bit strange, but it could even be centimeters per centimeter. It's possible to have different kinds of rates that are going to pop up in the kinds of questions that we're going to look at least. Okay, so next, what we're going to do is a little bit of warm up, and as I said, we're kind of talking word problems here, and this says word problems are hard because when we're learning new algorithms, often we make the numbers friendly and familiar, and sort of they work out, they're easy to work with, and then when we get into more real life modeling stuff, all of a sudden it's not quite that straightforward. And one thing you're going to notice is a lot of what we've done so far is things like this, and then we take the derivative, right, which is x, and y prime is short form for dy by dx, which is the derivative with respect to x. And that idea of what you're taking the derivative with respect to is something we've talked a little bit about, but becomes a lot more important in this unit. And it's sort of something we gloss over, like we just take for granted that it's always with respect to x, but it doesn't have to be. It could be with respect to any variable. And what happens then when you have expressions that have more than one variable, which you often have in word problems, and that's where these things do start to get a little bit harder. The great thing is that we've done a lot of work with implicit differentiation, and so we have been building skills over the last couple of months to work with this. So what we're noticing is this is with respect to t. And what I also might notice is, strangely to us, there isn't even a t in this question. That doesn't make sense yet, but it'll make a lot of sense once we get into the problems. So let's go ahead and do this. And if we think about our work with implicit differentiation, the derivative of a, capital A, is just dA by dt. Okay, and then pi is a constant, so it's just pi. So and r is a variable, so I'm taking the derivative of that, and I'm bringing the 2 down, so it's going to be 2 pi r, and then dr by dt. Okay, and on their own, it doesn't necessarily mean that much. This is just notation. We're just following steps. But when we start to get into problems, we're going to have to think about what these things actually mean. And I think that now is a good time to do this. We're going to talk about some tips and advice in a minute. But what is dA by dt? If t is time, okay, and we've differentiated with respect to time, this is the point. This is why this is powerful. If you remember what the d comes from in dA by dt, do you remember what it comes from? It's from delta. And what does delta mean? It means change. So dA by dt, dA is the change. Oh, and we didn't point this out, but what is this formula? It's the area of a circle, right? So it's a change in area. And what is dt? That's the change in time. So if this is the area of the radius, the area of a circle with a given radius at a particular moment, this equation right here will give us a relationship between how the area is changing over time as the radius is changing over time. So this is a formula that has rates in it, that relates rates to it. And the name of the unit is related rates, right? So I'm relating these two rates to each other. It still has an r in it, and we'll see why. And if we think about this, and actually next week we'll talk a bit more about this, about at a particular r, why that's important. But in general, that's what it's talking about. And thinking about units like this and what these things mean is, again, something people take for granted, and is so helpful to think about what the different parts mean. And what is dA by dt? It's the change in area over time. Say that in your head, that sort of thing. Okay, we'll come back more to that in a minute. Let's try another one. What do we notice here? What's different about this one? So it's volume, but we've got 3 variables. The v, that's fine on its own. That's just going to be dV by dt. But we've got r squared and h. So when I take the derivative, what's going to happen here? You might have a guess. And I hope your guess was product rule, because that's indeed what it is. So the first thing is pi r squared, and if I take the derivative of that, I get 2 pi r dr by dt, and then times the second thing, which is h, plus the first thing, which is pi r squared, times the derivative of the second thing. So h is just going to go away, just like if I was taking the derivative of x, the x would be gone, but I add in the dh by dt. So look at this, we've got all kinds of variables, and we got all kinds of things in here. And again, if you just visualize, this is formula for volume of a cylinder. So if you just visualize, how would the volume of if the dimensions of a cylinder were changing, how would the volume change, right? If the radius is getting bigger, the volume is going to get bigger. If the height's getting bigger, the volume is going to get bigger. So this is relating those things. And the radius and the height could both be changing, so we have to account for both of those. So that's why both of those things are in there. And there's also radius, and there's also height. There's lots going on in that one, obviously. But just in general, that's a little warm-up of how we would take the derivative. That's something we're going to want to get used to, okay? All right, here's our tips and advice on what to do. So I would have this copied down, written down, and I'd come back to it if I was stuck. I would start using these as, first step. What do you do when you come across a problem? We often get overwhelmed with problems, with new problems, and that's sometimes getting started or knowing where to start is the hardest part. And so there's a few little tips in here of little steps that are certainly doable. That'll help you get going, and a lot of them have to do with taking the word problem that you're given and turning it into a math problem. And then once it's a math problem, we typically will know what to do, hopefully, and then hopefully we execute it properly. So these aren't necessarily in order. Again, this is not an algorithm for solving these problems. This is just advice. These are just tips. But you may come up with an order, and to some extent, there's going to be a bit of a natural order in how you do things. One thing you're going to do as you're starting a problem, again, it might not be the first thing, but you are going to determine what everything, and that might only be one or two things. There might be lots of different dimensions. There might not, is being compared to. This is often time, but not always. And another way that we think about this is with respect to. So once you figure out what everything is changing with respect to, that's what you're going to differentiate with respect to. Okay. Something else we're going to do is identify variables. And we're going to see that happen when we do a problem. So that's something that we really want to be careful of. And there's going to be different kinds of variables. Sometimes we're going to have, variable R for radius, simple as that, but we're going to have different kinds of something new a little bit. So that's another part of the identifying variables, identifying the variables that are changing, that sort of thing. You also want to identify givens, very much like that's part of identifying variables. Is if you know some of the variables, then you add that in, and that's very similar to science, to physics, that sort of thing. We're going to identify any formulas that we might need, or hopefully the formula or equation that we're going to use to solve. And often we're finding a formula and we're going to take the derivative of that formula. So we're going to differentiate. And we differentiate usually early on, and that's going to obviously be a big part. If you're solving a problem and you haven't differentiated, you're probably not solving it properly, because this is calculus. So that's a pretty integral part of the process. But usually by the time you're differentiating, you got everything else done, and that's when you're kind of doing the solving part. Okay. Then we often substitute. Substitute looks different depending on what kind of question it is and what stage of the problem you're at. And then we're going to solve the final equation that we have. The whole thing is solving a problem, but I mean, we're going to end up with an equation that we're solving for the variable we're trying to find. And this is, again, after we've differentiated. Another thing, and again, these are not in an order, so something that can just be advice that you probably do early on when you're in the identifying variable stage, because it would be one of the variables, is what are you finding? What variable are you finding? What concept are you solving for? Like, what does it mean? That sort of thing. If you're asked to find the rate of change of the area, then you're finding dA by dt. This is the change in area over time. And then dr by dt, let's do that one, is the change in radius over time. Okay, and you could have anything, dl by dt, change in length, dw by dt, change in width, I mean, dv by dt, like all these things, dh by dt, all these things can come up. Okay, so those are just some tips, and I mean, there's going to be other things that come up here and there, but again, they're good ways of taking a bigger problem that can be overwhelming and breaking it down into smaller parts. And if you're not sure what to do, start thinking about what the variables are, and start thinking about what the variables would be if they were changing, that sort of thing. All right, our first question here, the volume of a sphere is increasing at 100 centimeters cubed each second. So something that we will talk more about, but that we notice, is that is a constant rate. So some things are changing at different speeds, but this is changing at a constant speed. The volume of the sphere is increasing at 100 centimeters cubed each second. Okay, it says find the rate at which the radius changes when it is 25. So what we're going to do here is we're going to start thinking about what these mean as variables. the volume of a sphere is increasing at 100 centimeters cubed each second. That's a rate. So that's the rate that the volume at which the volume is changing. That's dV by dt. This is such an important step that you can read through this question and recognize that that sentence is telling us what dV by dt is. And it's increasing, so it's positive. You don't have to put the positive, but sometimes it's going to be negative, so it's important to think about that. Positive 100, okay? And it also gives us a radius of 25, and you can include units here, might be useful. This is centimeters cubed per second. Okay, so this is with respect to time. Notice that it says each second, like it's telling us per second. So the per thing is what it's with respect to. That's what everything's changing in terms of. So this is definitely going to be with respect to time. Notice again, I have dV by dt for time. And what are we trying to find? We're trying to find the rate that the radius is changing. So we're trying to find dr by dt. Okay, or dr by dt equals question mark. That's another way of saying it. That's what we're trying to do. So what I want is, I need some kind of formula. I wonder what it's going to be that relates the volume of a sphere to the radius. And of course, it's just the formula for volume of a sphere, which is 4/3 pi r cubed. And so I take this formula, and that has the r in it that I know and the v in it that I know, and it relates those two things. It's about the volume of a sphere, so that's the right one, but coming up with the right formula is obviously the big part of it. And before I do anything else, I'm going to take the derivative. So dv by dt equals, the 3 comes down and multiplies, which is just going to cancel that 3, so I'm going to get 4 pi r squared and then dr by dt. And if you just stop and sit back for a minute and look, take a look at what we have here. We have a formula that's got that, it's got that, and it's got this. So I've got sort of 3 unknowns, 3 variables, but 2 of them I know. So what can I do? I can sub in and solve for the last one. And that's exactly what we're going to do. 100 equals 4 pi times dr by dt. And then I'm just going to move this all around, move it all over, and I'm going to end up with 100 over 4 times pi times 25 times 25. And 4 times pi times 25 times 25. Well, 4 times 25 is 100, so those are going to be gone. So I end up with dr by dt equals 1 over 25 pi, and this is centimeters per second. Okay, we want to think about units. And so therefore, the radius, blah, 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 right, is changing at 1 over 25 pi centimeters per second. Turn that into a decimal. That's a bit more useful probably, but there we go. So think about some of the things that we did over here. We were stating our givens and coming up with our variables and thinking about the variables that are changing and what that means, finding the formula, taking the derivative. Again, there those things are. But if you're trying to solve this and you're not thinking about that this is the change in volume over time, like what does that mean? If you're not explicitly thinking about that, then I think you're going to struggle with this. You're going to have a hard time, especially have a hard time whenever there's a new kind of question that comes up, okay? Okay, let's try another one. The length of a rectangle is decreasing by 1 centimeter each second, while the width is increasing by 2 centimeters each second. So the width is increasing twice as fast as the length is decreasing. Find the rate at which the area is changing when the rectangle is a square that has sides of 10 centimeters. Got a little visual for this one that hopefully will be a little bit useful. So it doesn't say what the dimensions start at, so I just picked a couple, but we can see what happens as I drag this slider. I get the length, which is these two guys, is decreasing. And so they start at 20. And when the length decreases to 18, the width has increased to 6. And so I can see that one is decreasing and one is increasing. and eventually they will approach a square. Okay. And it looks like those are actually backwards. It looks like the length is decreasing twice as fast, but you get the idea that that they're increasing, decreasing at different rates, and starting as a rectangle, and they're approaching a square, and eventually they're a square, and then they go this way. So this is what's interesting, is at all these different points in time, this shape has different areas, right? Different dimensions in different areas. The area is constantly changing, and the area might be changing at different rates. It's not necessarily changing at a consistent rate, and or whatever it is, the width or the length or whatever it is may not be in this case area, but then we're asked to find a specific one. So let's give this one a try. Let's see, the length of a rectangle is decreasing by 1 centimeter each second. Again, it's with respect to time, so that tells me dl by dt is -1 centimeter per second, while the width is increasing by 2 centimeters each second. So that's dw by dt is +2 centimeters per second. Find the rate. So find dA by dt when length and width are the same and they're both 10 centimeters. And we saw in the last example, I should have pointed this out, let's go back up. We saw that, we talked about this before, but we saw that this final derivative statement has this and has r and has dr by dt. Like, it's got all of them, right? It's got some changing variables, some not changing variables. So we need all those givens often for the final stage. Area of a rectangle, that's an easy one. The product rule, that's a pretty easy product rule, but it's dA by dt equals the derivative of the first thing, which is dl by dt, times the second thing, plus the derivative of the second thing, dw by dt, times the first thing. So there you go. And hopefully we have enough things that we can sub it and solve. I've got dl by dt, I've got w, I've got dw by dt, and I've got l. So I do, and I'm solving for dA by dt. No rearranging required here. So this is -1 times 10 plus 2 times 10, which is 10. 20 minus 10, so that's 10. So the area is increasing. This is, whenever it's positive, we take it for granted, but we're going to notice later on one of the answers is probably going to turn out to be negative, and we want to take the negative. We don't put -10. The answer is -10. That's not our therefore statement. We interpret it, and we turn positives and negatives into something meaningful. So in this case, this is a +10. It's a +10. So the area is increasing by 10 centimeters squared each second. The width is increasing faster than the length is decreasing, so apparently at that point in time, the area is increasing. All right, a couple more examples. Area of a circle. You'll notice that a lot of these are the same, so it does kind of become repetitive, but not all questions that we see are going to be the same, so don't get too comfortable with these. The area of a circle is increasing by 30 centimeters squared each second. Again, there we go. We're talking time, and it's giving us the change in area over time, which is +30 centimeters squared per second. Find the rate at which the radius. So find dr by dt when it has a length. Length, I think it means radius. Yeah, find the rate of the radius is changing when its length. That's what it's talking about, the radius. So find dr by dt when r equals 5 centimeters. Okay. So area of a circle. What do you think our formula is going to be? Formula for area of a circle. Take the derivative. Look at all those tips. Like, we're doing every single one every single time, right? Find the formula, take its derivative. I mean, there are sort of steps that you can eventually get used to and start to go through, but you know, you want to be careful memorizing too much, because then when you get a new problem that you have to think through, it's harder to do. Okay, let's sub in. So this is 30, 2 pi times r, which is 5, dr by dt So dr by dt is 30 over 10 pi, which is 3 over pi centimeters per second. Therefore, and it's positive again, therefore the radius is increasing by 3 over pi centimeters per second as the area is increasing by 30 centimeters squared each second. Okay, therefore, blah, blah, blah. All right, I believe this is our last example, although there's a couple parts to it. Sides of a cube are increasing by 10 centimeters each second. Find the rate at which the area is changing when the side length is 1 meter. So one thing I noticed is this is centimeters and this is meters. We want to be careful of that. The sides of a cube. Find the rate at which the area is changing. So I guess it's talking like surface area there. And surface area of a cube, what's that going to be? Well, a cube has 6 sides that are all squares and they're all the same square. So the area is going to be 6 times the side length squared. Okay, let's see. Before we go any further, what do we have? We're given find the rate at which the area is changing when the side length is 1 meter. So side length equals 1 meter or 100 centimeters. The sides of the cube are increasing by 10 centimeters per second, so that's ds by dt equals 10 centimeters per second. Okay, and if this is question A that we're doing here, we are finding dA by dt. Okay, and so so we got to differentiate. Remember what I said, if you've solved the problem and you haven't differentiated, you're probably doing something wrong. D12s ds by dt, and so dA by dt equals 12 times the side length, which is 100, times ds by dt, which is 10, and that works out to 12,000 centimeters squared per second. Next question is a little bit different because it says find the rate at which the area is changing when the cube has a volume of 4,000 centimeters cubed. What's that telling us? Again, see, this is some problem solving stuff. So to find the rate at which the area is changing, I do need this. So I don't want to use the volume formula and take the derivative of that because that doesn't have dA by dt in it. So why is it giving me the volume? Well, what I need for this is I need ds by dt, which we have. We were given that in the beginning. And I need s. So if I'm given the volume, I can use that to find s. So that's what this question is all about. B, so volume is length times width times height, but they're all the same. So s cubed in this case. So 4,000 is s cubed, so s is the cube root of 4,000, whatever that works out to. Okay, so now I can do this again. dA by dt, we already found this, is 12s ds by dt, and that is 12 times s, which is the cube root of 4,000, times 10. That part didn't change, which is 120 times that, and it works out to about 1904.9 centimeters squared per second. Okay, and I believe that is all the examples that we have. So those are some different types that have to do with measurement, area, volume, surface area, those kinds of things. Those are the first problems that we looked at. But it gives you a general idea of, they're nice and simple, you know, pretty straightforward. You gotta know the formulas, so look those up if you need them. But thinking about what this actually means, that's what we're starting to get used to before the problems start to get even a little bit harder. Okay, good luck.